Welcome all. Myself Ashish Joshi. I am working at Photogrammetry and Remote Sensing Department at IIRS Dehradun. Today I will give the lecture on the overview of SAR data processing. So in this lecture, we will learn about the basics of radar and SAR concepts. And after that, we will learn about the basics of SAR image formation, which is also called the level 0 processing. After that, the basics of SAR post-processing, which is also called the level 1 processing. So what is radar? Radar transmits the microwave electromagnetic radiations, which is also called the pulses, towards a scene through the transmitter. Means this is a radar. It will transmit the pulse towards the Earth's surface, and these pulses will interact with the targets in the Earth's surface. After that, the pulses are backscattered towards the SAR sensors, and the energy is gathered by the SAR. It observes the strength, means amplitude of the signal, and the time delay, which is also called ranging. Means in the radar, we will get two components. One is the amplitude and second is the range to the sensor. So how the range is calculated in radar? So from our formula, time is equals to distance upon speed, we will calculate the time delay. Time delay is given by the distance, which is given by the 2r. Okay, why this 2r? Because the pulses will travel this distance twice the range. Okay, so the distance, total distance is traveled is equals to 2r, and it will travel with the speed of light. So the speed is given by the c. So the time delay is given by the 2r by c. Okay, from that we will get the range as c t by 2. Okay, so this is called the range calculated through the time delay. So this is the concept of the radar. Means radar will transmit an electromagnetic wave. This electromagnetic wave interacts with the Earth's surface, and some of the energy is backscattered towards the sensor, and the sensor will sense the amplitude and time delay of the signal. From the time delay, it will calculate the range. Radar has mainly two components. One is the transmitter, second is the receiver. From the transmitter, it transmits the electromagnetic radiations, and from the receiver it receives the electromagnetic radiation. Okay, then it is actually illuminate the Earth's surface like a torch beam, because radar is an active sensor, so it will illuminate the Earth's surface just like torch. So like torch in the night, we will illuminate the dark area. In the same way, the radar will illuminate the Earth's surface through the radar beam. So this radar beam is same like a torch beam. Okay, and this angle is given by the theta, and which is called the beam width. And this beam width is calculated through the mathematical formula k lambda by L, where lambda is the wavelength of the electromagnetic radiation and L is the length of the antenna, and k is the constant which is determined by the shape of the antenna. So this is the formula of the beam width. So we have the in the radar two components, transmitter and receiver, and the beam width is given by this formula k lambda by L. Now coming to the synthetic aperture radar. Now simple radar will not produce the images. To obtain the images, we will use the synthetic aperture radar, which will use the concept of the synthetic aperture. So synthetic aperture radar is also called the imaging radar, because it will generate the two-dimensional image. A simple radar is not able to form a two-dimensional image. So what is SAR? SAR is a side-looking radar system which makes a high resolution images of the Earth surface. Okay, so if at this point, if we will consider it is a radar, then with the motion of this radar, it will illuminate the Earth surface in this direction. So this direction where it moves is called the azimuth direction, and this is called the radar footprint, which is illuminated by the radar beam. And at some angle, it will illuminate towards the radar, which is called the loop angle. Okay, so the continuous strips of the ground surface are illuminated to one side of the flight direction. So it will illuminate the one side of the flight direction. This signal is recorded, and the digital signal processing techniques in the ground are used to focus the image and obtain the high resolution images. So the signal is recorded as a raw data, and some in the ground again the data is given, and this data is processed in the ground data processing system. So we should use some signal processing techniques to process the SAR raw data. So this is how the SAR raw data will look. Okay, so this direction is called the range direction, and this direction is called the azimuth direction. As the SAR moves in this direction, we will collect different electromagnetic radiation or pulses, and we have a two-dimensional image. Okay, so this is the SAR raw data. So the across track direction, this is called the range, and this direction is called the azimuth. So SAR has the two resolution. One is called the range resolution, and second is called the azimuth resolution. So because the normal radar will not produce the images, so we will have to use some principles to obtain the high resolution images. So the fine range resolution is achieved by using the pulse compression technique, and the fine azimuth resolution is achieved by using the synthetic aperture concept. A combination of these two principles enables the high resolution in both range and azimuth direction. Means the SAR has two resolution, range and azimuth, and to get a high resolution images, we have to use the two principles. One is called the pulse compression technique, and second is called the synthetic aperture concept, to get a high resolution images from the radar sensor. Now we will see some basic terms of the electromagnetic wave or pulse. So first is the wavelength. Wavelength is the distance between the successive crest of an electromagnetic wave. So if this is the electromagnetic wave, then this distance is called the wavelength. Means two successive crests is given by the wavelength. Okay, and what is the frequency? The number of the curves that passes a fixed point in a given amount of time. Okay, so that is the frequency, and it is given by the formula C is equals to lambda nu, or nu is given by the C by lambda. Nu is the frequency, C is the speed of the light or electromagnetic radiation, and lambda is the wavelength. Okay. And third term is the pulse width. What is the pulse width? It is the time duration of the pulse. How much time it is taking? It is called the pulse width. And fourth is the pulse repetition frequency, which is also called the PRF. The number of pulses transmitting per second. Okay, a number of pulses which are transmitting in a 1 second is called the pulse repeating frequency. And inverse of the PRF is given by the PRI. Means what is the time between two pulses? If radar is transmitting a number of pulses, so what is the time difference between these two pulses is called given by the pulse repetition interval, and the time duration of the pulse, single pulse, is called the pulse width. And what is the sampling frequency? The frequency at which the pulse is sampled for the conversion of the pulse from analog to digital. So it is given by the Fs into time. Means Number of samples is given by the sampling frequency into the pulse width. So this is called the sampling frequency, means the frequency at which pulse is sampled. Means if we have any analog signal and we want to do the sampling, so at which frequency we are doing the sampling, it is called the sampling frequency. Okay, so this is if we can consider the electromagnetic wave. So there we will consider this is a low frequency electromagnetic wave and this is a high frequency electromagnetic wave. Means the lambda is higher here for the low frequency and the lambda is very much short for the high frequency electromagnetic wave. Now the question is arises how to get a better range resolution, because radar is not giving a very fine range resolution. So to get a better range resolution, what we will use? Okay, so if we will consider this one, this is the pulse width. Means first pulse, second pulse, third pulse, fourth pulse, and this is the reception window. Means at this time the radar will receive the signal. Okay, here it will transmit and in this window it will receive the signal. Okay, so what is the time between these two pulses is called the PRI, and the formula is PRI is equals to 1 by PRI. So if the radar is seeing the two targets, means if this is the radar and it is seeing two targets T1 and T2. Okay, and the distance between these two targets is from the SAR sensor or radar sensor is given by the R1 and R2. Okay, so from the formula of time delay, the time delay is given by formula 2R by C. Okay, so if this is the two pulses and the target response is given in this reception window, means this is the received echo from the first target and this is the received echo from the second target, then the radar will discriminate these two targets as two separate targets when the time difference between the two targets is greater than the pulse width. Okay, means the radar will discriminate these two targets as separate targets when the time difference between these two targets is greater than the pulse width. So this is the basic principle. And then from our mathematical expression, this 2R2 by C minus R1 by C should be greater than tau. Okay. So from previous slide, we will see this is the two targets echo. This is blue one is the target 1 echo and this is the target 2 echo. Echo means the return signal. So this is the return signal from the target 1 and this is the return signal from the target 2. And the combined signal will look like this one. Okay. So this when it is received by the radar, then it should discriminate these two targets as the separate target. So what is the principle it will follow? This distance should be greater than tau. Okay. And from this formula, the delta R should be greater than C tau by 2. So this is the condition to discriminate the two targets as separate targets. So delta R means distance between these two targets should be greater than C tau by 2. Now tau if we will take as 20 microsecond. Okay. So if we will take the pulse width of 20 microsecond, then we will see delta R should be greater than, with the formulation, it should be greater than 3000 meter. Or we can say delta R should be greater than 3 kilometer. Means if the distance between these two targets is greater than 3 kilometer, then only this radar will differentiate these two targets as separate targets. So this is a very coarse resolution. So how to get a fine resolution? So if we will use the electromagnetic radiation of 20 microsecond, then delta R is given by 3 kilometer. Means the range resolution is given by the 3 kilometer. Then sensor will separate these two targets if distance between two targets is greater than 3 kilometer, which is a very coarse resolution. Okay, so this is a problem. Then how to solve this one? So if delta R is greater than C tau by 2, so we want this delta R should be as low as possible. So decreasing this delta R, what we will do? We will decrease, we can decrease this tau. Means if we decrease this tau, then this delta R will decrease. Now if we decrease, then it also reduces the energy in the pulses, because the average power is given by the transmitted power tau into PRF. If we will decrease this tau, then the average power or the signal power will decrease. So that is not a solution. Means we cannot decrease this tau up to some level. Okay, so what is the solution? Now solution is the linear frequency modulated or LFM signal. What is that? Means normal pulse is have the fixed frequency. Okay, this is the normal electromagnetic wave. But LFM is a longer pulse with varying frequency. Okay, so we will see this pulse has a fixed frequency, but LFM has the varying frequency. Okay, means it is varying within the electromagnetic wave. Okay, so this is the solution for getting a high resolution in the range direction. So here we can see this bandwidth is independent of tau. It is given by only the delta F. Okay, so a pulse compression technique is used to get a better range resolution. Okay, so what is the pulse compression technique? So this is the linear frequency modulated signal. This is called the real part of the chip. This is called the imaginary part of chip. This is the unwrapped phase, and this is the frequency plot. Okay, so this is some of the properties of the LFM signal. So what is the pulse compression technique? Okay, so in the earlier slide, I have told you to get a better range resolution, we will use the LFM wave. Means LFM wave is the linear frequency modulated signal with the varying frequency. Okay, so what it will do means radar will transmit the LFM signal, and in the ground we will use the match filtering technique to compress the this LFM wave. Okay, so what is the match filtering? The received pulse is multiplied with the complex conjugate of the transmitted pulse in the frequency domain. Okay, means this is the reference signal, and if this is the target echo 1 and this is target 2 echo. Okay, then what we will do, we will multiply with the complex conjugate. Okay, with the complex conjugate of this signal in the frequency domain. After this, if we multiply, then the response of the target is given by the sinc function. So we will see this target is now compressed. Okay, now this is the first target, compressed target, and this is the second compressed target. So this is the this technique is called the pulse compression technique. In this, what we will use the linear frequency modulated signal, and then it is compressed by using the match filtering technique, in which we will multiply the signal with the complex conjugate. Okay, so this is called the pulse compression technique. So by this pulse compression technique, we will get a better range resolution. So how the better resolution we will get? Then we have already seen that delta R is given by C tau by 2, or this is given by C by 2b, because tau is the inversely proportional to the bandwidth. So the range resolution is given by the C by 2b, means B is the bandwidth of the signal. So if the bandwidth of the signal is 250 megahertz, then we will get the range resolution of around 0.6 meter. So what we have seen, by using the pulse compression technique, the 3 kilometer range resolution is now is equals to the 0.6 meter resolution by using this pulse compression technique. Okay, so from the pulse compression technique, we have achieved the desired range resolution, which is only depend on the bandwidth of the transmitted signal. Now, if we will use the bandwidth of the 75 megahertz, we will get the resolution of 2 meter. If we will use 150 megahertz, we will get a 1 meter resolution. If we will use the bandwidth of the 750 megahertz, we will get a range resolution of the 0.2 meter. Means the range resolution is inversely proportional to the bandwidth of the signal. If we will increase the bandwidth, we will get a better range resolution. So the better range resolution is required to see the small target. If the any target or any feature is very much small, then if the range resolution is small, then we will able to discriminate these small features. Okay. Now, using the pulse compression technique, we have achieved the desired range resolution. But for the azimuth resolution, we have to use some other concept, which is called the synthetic aperture concept. Okay. Now, in the azimuth direction, the azimuth resolution is given by the azimuth beam width into the R. R is the slant range, and beam width is equals to the lambda by L. Okay. So how much azimuth resolution we will get? So if we will put R is equals to 800 kilometer, means for the satellite case, if we can take the low Earth orbit as a satellite, then R is around 800 kilometer. Lambda is we can take from the microwave region 3 centimeter, and L is equals to 12 meter. Okay, then the azimuth resolution is coming around 2 kilometer. So it is very much coarse. Okay, because we are using the lambda in the microwave region, then we are getting a very coarse that azimuth resolution. But for the optical sensor, optical satellite, we will get a better resolution because the lambda is very much small there. Like the view in the optical visible range, we will have the lambda is equals to 0.4 micrometer. So we will get the resolution of 0.7 meter in the optical scenario. But because the wavelength is very much larger in the microwave region, so we are getting a azimuth resolution of around 2 kilometer. Now, how to solve this problem means how to get a better azimuth resolution. So if we will have means how much length of the antenna we will have to get a better range resolution. So from the formula, L is equals to lambda R by azimuth resolution. From the previous slide, we will get the L from this formula. L is given by the lambda R by azimuth resolution. So lambda R by azimuth resolution. So we can do some calculation, means what is the size of the length of the antenna, so that we will get the azimuth resolution of 0.6 meter. So if we want the azimuth resolution of 0.6 meter at a height of 800 kilometer and with 3 centimeter wavelength, then the length is equals to the 40,000 meter, means 40 kilometer. So if we want azimuth resolution of 0.6 meter, we have to have 40 kilometer length antenna, which is impossible to carry in the space. So how to solve this problem? This problem is solved by the synthetic aperture concept. Means the radar is forming a virtual antenna of very large length. Because this radar beam sees this target for a longer duration of time. Okay, means we will see this target has been seen by this radar for a quite longer time. So this is appearing as a long antenna it is forming. Okay, so this is called the synthetic aperture concept. Means with the motion of the SAR, it is forming a longer antenna. Okay, and for the longer antenna, we will get a better azimuth resolution. Okay, so this is called the synthetic aperture concept. That the target is observed by the radar from multiple locations along the satellite path, and this technique is based on the fact that target stays in the beam for a significant amount of time. So this time duration is utilized to form a longer antenna. Okay, and this motion of the SAR will form a virtual antenna, which is called the synthetic array. So with the motion of the radar, it will form like this target is seen by a multiple radar system. So it is from a longer antenna. Okay, this multiple location is called the synthetic aperture, and this synthetic aperture is given by the formula 2 lambda r by L. This is called the synthetic aperture length. Means this target, due to the motion of the SAR, it is like it is seen by the multiple radar location. Okay, and this is also with the motion of the radar, it is forming a azimuth LFM. Means I have told you in the range direction we are transmitting a LFM, but in the azimuth direction it is formed by the motion of the sensor. With the motion of the sensor, it will form a azimuth linear frequency modulated signal. Now this improved azimuth resolution is given by the R is equals to azimuth beam width, or LS is equals to 2 lambda R by L. If we substitute this LS value here, then we will get the azimuth resolution is equals to L by 2. So for the normal SAR, we will get the resolution of L by 2. So if the length of the antenna is 12 meter, we will get the azimuth resolution of the 6 meter. Okay. So this is the basic concept of the synthetic aperture. Means from the in the space, we will utilize the motion of the radar sensor to have a synthetic aperture, and due to this synthetic aperture we have a longer antenna, and from the longer antenna we will get a better azimuth resolution, which is equals to the half of the length of the antenna. Means if the real antenna length is equals to 12 meter, then the improved azimuth resolution is given by the 6 meter. Okay, so this is the synthetic aperture concept. So up to now we have learned about LFM is a longer pulse with varying frequency, and higher resolution in SAR images is achieved by the pulse compression and synthetic aperture concept. Okay, so these two concepts we will use for the high resolution images obtained by the SAR. The SAR range resolution depends on the pulse bandwidth, which is given by the range resolution is given by the C by 2B. It is depend on the bandwidth. Higher the bandwidth, better the resolution. SAR azimuth resolution depends on the antenna length. So azimuth resolution is given by the L by 2. Means if the real antenna length is of 12 meter, then we will get a resolution of the azimuth resolution 6 meter. Radar azimuth beam width is given by the lambda by L, and radar azimuth resolution is given by the lambda R by L. So this is the radar beam width formula, and this is the SAR resolutions formed, high resolution images. Now in the data processing, we have many challenges in the SAR. So first challenge is the range cell migration, and because in the SAR, as this radar moves in this direction and the SAR beam is in this direction, then the range to the target will follow this hyperbolic equation. Means at any instance of the target, the range is given by this formula. R0 is the minimum slant range, VR is the effective velocity, and this is the time. Okay, so this is given by this formula, and this is called the hyperbolic equation. So from in the target in the signal memory, the same target response is written like this in this fashion. Okay, it is following the hyperbolic equation. So a single point target in the azimuth is spread in the azimuth direction like this curve. So this point target in the azimuth, it is spread in the azimuth direction with a curve. So this is called the RCM effect, means range cell migration, because this is not a particular position and it is migrating from its position in the azimuth direction. Okay, so this is called the range cell migration, and this we have to correct in our raw data processing. Okay, so this is the first challenge we have to do in the SAR data processing. Another effect is called the Doppler effect. Doppler effect, what is Doppler effect? When an observer moves with respect to the source a shift in frequency is observed known as Doppler frequency. Okay, because and the SAR is also moving, and if we will see the target is fixed, then there is a shift in frequency. That shift in frequency is called the Doppler frequency. So that Doppler frequency is given by formula 2Vs sine theta of squint angle by lambda. This is the target satellite velocity. This is the angle made by the SAR sensor, which is called the squint angle. So this is the formulation. So with the movement of this, we can see the truck. This is towards this direction. So here the frequency is increasing, and here the frequency is decreasing. So for in this Doppler, we will have a LFM kind of signal, means we have the varying frequency, means here the frequency is increasing, here frequency is decreasing. So with the motion of the SAR, we have a Doppler effect, and this Doppler effect will give the LFM in the azimuth direction. Okay, because we need LFM in the range direction, that is achieved by transmitting the signal. But in the azimuth direction, with the motion of the SAR and the Doppler effect, we will have this LFM in the azimuth direction. Okay, so this Doppler shift is given by the formula 2Vs sine theta squint by lambda. Now this squint angle, what is this squint angle? The squint angle is the angle made by the slant plane vector with respect to the zero Doppler plane. Okay, means if the SAR, if any radar or SAR is seeing this target, then at this position it have the zero Doppler, and but the radar is making the angle with this zero Doppler is called the squint angle. So this is called the squint angle, means with respect to this, how much angle is changing. So this is called the squint angle. So this is zero squint, this is a squint angle with some angle theta. Okay. So in the actually in the SAR data processing, we have to calculate the Doppler centroid. Okay, because we have the Doppler effect in the SAR, so we have to calculate the Doppler centroid, which is used in the SAR data processing. So Doppler centroid is defined as the Doppler frequency subtended by the target at the aperture center when the beam center crosses the target. So we will see in this diagram as the sensor position is changing. So here we can see the range is high. Here Doppler is becoming zero, and then it is again increasing. So first, and the Doppler will decrease, the Doppler will become zero, and then Doppler will increase. In the same way, the frequency first start decrease, become zero, and it will then increase. So this is the target response, and this is the frequency curve. Means first the frequency will decrease, it will become zero, and then it will start increasing in the negative direction. So this is called the Doppler history of a point target as the sensor passes. So in the SAR data processing, we have to calculate this Doppler centroid, means what is this position of the sensor when it has the zero Doppler. So that is called the Doppler centroid. Means what is the Doppler when the beam center crosses the target. So what is the Doppler at this position? So how to do from the image? From the image, but what is the formula? The frequency of the peak of the Doppler magnitude spectrum is estimated from the power spectrum of the data. Means if we have the data, then first we have to find out the power spectrum of the data, and where is the peak of the power spectrum. That is, we can calculate as the Doppler frequency. So that is called the zero Doppler. So first we have to find the power spectrum of the data, and then we have to find the where it is the maximum is occurring, and that maximum position is given the Doppler centroid. So that is needed for the SAR image formation techniques. So there are some signal processing concepts. Okay. So first concept is the time domain is converted to frequency domain through Fourier transform. Okay, so we have to do the fast Fourier transform, or we can take the FFT of the image to transform from the time domain to the frequency domain. So why we have to do in the frequency domain? Because the formula the convolution in the time domain is equal to the multiplication in the frequency domain. If any two signals which is convolved in the time domain, if we do the processing in the frequency domain, then we have to just multiply these two signals. So that is the need to do in the frequency domain, because our SAR signal convolve with the targets and return back to the signal, means there is a convolutional happening in the SAR data processing. So what we will do, we will transform the SAR data from time domain to the frequency domain, because there the time domain, the convolution is equals to the multiplication in the frequency domains. This is the formula of the convolution of two signal in the as expressed in the mathematical form. Okay, so we have to understand two important concepts, means how to transform from time domain to frequency domain. Just we have to take the FFT. Why we have to do the Fourier transform? Because the convolution in the time domain is equals to the multiplication in the frequency domain. So this is some of the basic steps of the SAR image formation. Means this, you can see this is the SAR raw data. So it is of very coarse resolution. As I have told in the earlier slide, the range resolution is also very much coarse, and the azimuth resolution is also very much coarse. Okay. So what we will do, we have to do some data processing from in the raw data. So there are some important concept. Means first is the important concept is called the range compression, then RCM correction, and then the azimuth compression. Okay. So this is the basic flow chart of the range Doppler algorithm for the low squint data. Okay. So first we have to do the range compression, then we have to take the azimuth FFT, then RCM correction, then azimuth compression, and then azimuth IFT. Yeah. Okay. So this is in the raw data of the SAR signal. Okay, and this is called the focus data. So this is called the level 0 data, and this is called the level 1 data. So and any SAR sensor like pulsar or radar set, either they will provide in this form or in this form. If the data is in this form, this is called the level 1 data. So we have to do the level 1 processing. But if we have the level 0 data, then we have to do the raw data processing. So in the raw data processing, we have to do these already. We have to do these steps for the raw data. If we are providing directly this level 1 data, then we don't need to do this type of steps. Then we will directly use the product, and we have to generate our ortho rectification and some other products, which is called the level 1 processing. Okay, so how the SAR raw data will look like? So this is called the for every pixel of the SAR image consists of the real and imaginary part, which contains the amplitude and the phase information. Unlike the optical sensor, the SAR has the complex data, means it has the real part as well as the imaginary part. So we can calculate the amplitude and we can calculate the phase information. How the amplitude is calculated? It is calculated as square root of real square plus imaginary square, and phase is calculated as tan inverse of imaginary part by real part. Okay, so the SAR raw data will consist of two images. One is the real image and one is the imaginary image. Just like the optical sensor, we have the different bands. In the same way, we have two bands in the SAR data. If it is in the complex form, one band is called the real part and second band is the complex part. So both level 0 and level 1, it is of the complex nature. Okay, so if raw data is of complex data, then we have to do some signal processing technique like range Doppler algorithm to process the data. If it is in the level 1 SLC, then we have to do some of the level 1 processing. Okay, so the raw signal is a form of amplitude into the exponential of j of phi. Phi is our phase, this is the amplitude, and this is the sine plus I cos theta. Okay, this expression is sine theta plus I cos theta. So this is called, A is called the amplitude, intensity or power is given by the A square, and phase given by the phi. So first part in the range Doppler algorithm is the range compression. So we know this reference LFM means what we will know means what is the reference signal. So this is the reference signal. This reference signal we will use to compress the our data. So that is called the match filter. So match filter is generated by this formulation. E, because I have already told this is the match filter, and we have to multiply this match filter with the complex conjugate of the data. So match filter is generated by the formula J pi of, this is called the range chip or the slope, which is given by the B by tau. B is the bandwidth of the signal and tau is the pulse width. So this is some of the parameters which is given by the SAR, which is called the pulse duration, bandwidth, sampling rate, light velocity, and chip length. So these all parameters we will get from the SAR data. So from that SAR data, we will make our match filter by using this equation. Okay, so the equation is look like this one. Then this match filter is multiplied. So how the range compression will we do? We have to do FFT in the range direction. Means in the range direction, we have to do the FFT and transform the data in the frequency domain. Then FFT of the transmitted LFM pulse is performed. Means this is the match filter we have generated. Then we have to take this FFT also. Means we have to take the FFT of the data in the range direction, then FFT of the LFM pulse. Then just we have to do the match filtering. Means we have to multiply the conjugate of the LFM pulse with the raw data in the frequency domain. Okay, so this is the part of the range compression. Means we have to generate the match filter. Then this match filter we have to do the FFT. Then we have to do the FFT of the data. Then we have to multiply these two in the range direction. So that is called the range compression. And again we have to do the inverse FFT to convert back to the time domain. So from the FFT we are transforming from the time domain to frequency domain. From the inverse FFT we are converting from time domain to from frequency domain to the time domain or the range domain. So this is the raw data. So after the range compression, how the data will look like this? It will look like this data. So why this is behaving like this? Because they are the point targets. One point target here, one point. But due to the expansion in the azimuth direction, the whole target is expand in the azimuth direction. And due to the RCM effect, because the range, every target is following the hyperbolic equation. So every target is not as a straight line, but it is having the non-linear hyperbolic shape. Okay, so every point target is spreading in the azimuth direction and as a hyperbolic shape. So what is the next step? We have to focus in the azimuth direction, and also we have to make as a straight line, and then we have to compress it. So second step is the range cell migration correction. Means this hyperbolic path or the non-linear path, we have to make a straight line. Okay, so what we have to do? We have to do our range cell migration correction. So how it will do? After the range compression, and azimuth FFT is performed to make a range Doppler domain. So okay, so the algorithm is called the range Doppler. So in this, what we have taken the range in the time domain and now azimuth as a frequency domain, because we have taken the FFT in the azimuth direction. So this is called the range Doppler plane, because range in the time domain, but this is azimuth direction, it is in the frequency domain. Then the RCM correction is performed in this domain. All target trajectories in the same range are transformed into the single target through the interpolation. Means we have to interpolate each position to make a single line. So and this we have to find how much it is the deviation it is occurring. That deviation we have to interpolate, and we have to make this a straight line. So after the RCM correction, what we are doing, we are making each point target as a straight line. So now after the RCM, we have to have done the correction, and each of these non-linear lines is transformed into the straight line. So each of the target is now straight and but expand in the azimuth direction. So this is called the RCM corrected image. And we have also to estimate the Doppler centroid in this domain, in range Doppler domain. So final step is the azimuth compression. Now we can see this is the image, but the targets are it is elongated in the azimuth direction. So what we have to do, we have to perform the match filtering in the azimuth direction and compressing this signal to a single point. So what we have to do, after the range direction correction, match filtering is performed in the azimuth direction using the match filtering technique. Okay, here, but how to make the match filter? We have to make the match filter like this one. So Ka is called the it is called the azimuth FM rate. So this azimuth FM rate is given by the 2v square by lambda r. So this is the radar velocity, this is the slant range, this is the wavelength. So we have to compute this azimuth FM rate, which is called the Ka. So this is called the match filter, and this is called the Doppler centroid. So this is the Doppler centroid. So this match filter, what we have to do, we have to multiply in the azimuth direction. So in azimuth compression, azimuth FFT is performed in the azimuth direction, and then LFM pulses is constructed with azimuth FM rate and FFT is performed. But finally, we have to do the inverse FFT, and we have to convert the whole data again into the time domain. Okay, so this is the whole range Doppler algorithm, in which we have to basically do the 3 steps. First is the range compression, then we have to do the RCM correction, and after that we have to do the azimuth compression. So doing these 3 processes, we have to compress the data and we have to process the entire raw data. So we have different algorithm for different modes, like strip map. We have to have the range Doppler and chip scale. For spotlight mode, we have the omega and extended chip scale, and the SAR we have the Spacken algorithm. Okay. Now this is called the level 0 processing. So after the level 0 processing, the image is formed. Now what we have to do, because at the after the image is formed like this is in the slant range geometry. So it is not in the ground range geometry. Okay, so the ground range and the slant range is given by this relation. Ground range is equals to slant range by sine theta. Theta is the angle of incidence or look angle. So if this is the look angle, then this is called the incidence angle. Then if the terrain is flat, then the look angle is equals to the incidence angle. So the ground range is equals to the slant range by sine theta. So we can see this image in the slant range, it is little bit compressed. So it is not geometrically corrected. So we have to do some geometrical correction. To means we have to do this formulation and we have to correct this one. Now this is the ground range product. So we can see the differences in the geometry. So this is the slant range, because the image, every point in the ground is written in this plane. Okay, so if this is the plane, so level 0 processing we have to do in the slant range only. So every point is written in the slant range, and because of this formulation, it is going compressed. So if the slant range image is generated, then every target is compressed in the slant range geometry. So after doing the slant to ground range conversion, we are making the SAR image geometrically correct. After that, because the image which we are getting, it is not georeference, or we don't know the latitude and longitude of the image pixel. So that is what we have to do. We have to do the SAR geolocation algorithm. Geolocation is the process of the calculation of the geographical coordinates or latitude and longitude of an image pixel. Means if this is the image pixel, then we have to find the latitude and longitude of the image. So SAR geolocation will follow these 3 equations. First is the Earth ellipsoid equation. This is called the range equation, and this is called the Doppler equation. These 3 equations are the basic equation for solving the unknown XYZ point of the target. So solving this, we have to find out the XYZ of the position, and here XYZ is called the unknown target position. This is X set, Y set, Z set is the our sensor platform is SAR position coordinates, and this is called the velocity. From the SAR auxiliary parameters, we can get this the satellite position and velocity. This state vector will contain time, x, y, z, and velocity vector. So this state vector we know. Now this is the unknown point, and we will first form the range equation. This is the range equation, and this is the Doppler equation, and this is called the Earth equation. So from these three equations, we will solve these three equations, and we can solve for this x, y, z. This non-linear equation is give the solution by using the numerical formulation. Okay, so after getting this ij to a particular lat long, so this is called the image to ground geolocation. Means for every ij, means any sample or row position, or any, we can say, the row and column position, we will get the lat long of that point. So that is called the image to ground location. Means we are geolocating at. So this is called the forward geolocation. Means for each image pixel, we are geolocating the point, lat long to a point. Again, if we know the lat long, we have to give the, but from where, from the SAR image it is coming, that is called the backward geolocation. Okay, in the backward geolocation, what we have to do for a given lat long in the geographical plane, input scan pixel in the SAR slant range image is computed using the range Doppler equation. Okay, so in both formulation from image to ground and ground to image, we have to use the range Doppler equations for geolocating the target. Okay, so this is the basic formulation of the SAR geolocation steps. So next step is the SAR geocoding. Means what the image we are getting in the after the raw data processing, it is not in the map geometry. Means it is not oriented towards the true north or south. Okay, so what we have to do, we have to do the orientation of the SAR image to a particular map geometry. So how to do it is done by the process which is called the SAR geocoding. So SAR geocoding is the process of sampling the slant range image from the SAR coordinate system to the geographical coordinate system. Because the SAR raw data, or after the process also, it is in the slant range geometry. After that, we can also convert in the ground range geometry, but it is not having not in the geographical coordinate system. Means it is not in the lat long domain of the like other SAR sensors. So what we have to do, we have to do the different types of geocoding. First is called the ellipsoid correction, and second is called the terrain correction. In the ellipsoid correction, what we have to do, we have to do this correction using the earth like the average height. But for the geocoded terrain correction, we have to include the dam also. Dam, what is dam? It is called the digital elevation model. So for correcting all the geometrical correction, what we have to consider the dam for the geocoded terrain corrected, which is also called the ortho rectification. But for correcting the geometrical correction using a single average height, that is called the geocoded ellipsoid correction. In this correction, what we will assume the average height of the terrain, and then we can do the correction. But in the geocoded terrain correction, we have to use the dam to correct the data. Okay, so in the SAR geocoding, we have to transform from the slant range geometry to the map geometry by computing the lat long using the SAR geolocation technique, and then correcting to with the help of the terrain. Terrain we can get from the digital elevation model. If the digital elevation model of any area is available, then we can do the geocoded terrain correction. Otherwise, we will use the terrain geocoded ellipsoid correction using the average height of the sea. So after the all this process, what we will get the geocoded image. Okay, so this is called the raw data. So this is the raw data that we have seen as an input. Means this is the raw data which have a very coarse resolution, and this is the real part of the data. So after doing the range Doppler algorithm, what we have done the focusing. Means after doing the range compression, azimuth compression, and the range correction migration, we have this image which is now we can visualize, but it is not have the proper geometry. So this is called the level 0 image, and this is called the level 1 image or detected image in the slant range geometry. So here we cannot see any target feature in the image. So after doing the range compression, azimuth compression, and the range cell migration, we have focused this image. So after focusing, we will analyze this image. But for the real-time application of anything, we have to have the exact position of this, and it should be geometrically correct. Geometrically correct means if we overlay this image to any other GIS platform, then it should match with the features of other image. Means other image, we can have other image like optical data, we can have the hyperspectral data, we can have the multispectral data. But this image and this image is still in the sensor geometry. Means sensor geometry means it is in the range direction. This is the azimuth direction. So it is in the rectangular form in the sensor geometry. So what we have to do, we have to still do some of the corrections. What are that correction? That is called the geometrical correction. That geometrical correction, how to do? We have to do the principles of the geolocation and geocoding. In the geolocation, what we have to do, for image pixel, for every image pixel, we have to calculate the latitude and longitude using the three equations. Means first is the range equation, second is the Doppler equation, and third is the ellipsoid equation. These three equations can be used for the SAR geolocation purpose. After doing the SAR geolocation, what we have doing, we are having the ij position and we have the lat long of this position. Okay, so now after doing the SAR geolocation, we have for each image pixel we have some lat long. Okay, but still the image is not sampled to the geographical plane. So if we after the SAR geolocation and if we have the terrain of the earth surface also, then using that both things we can resample this data from this SAR sensor geometry to the geographical data. Means now this is called the geocoded image. Means you can see this feature is now coming here because SAR is an active sensor and it can image both right and left, and it can also image in the ascending pass and the descending pass. So we have many much flipping in the flipping of the features. Means it can be flipped either in the vertical direction or in the horizontal direction. So any of the feature in the slant range geometry can be flipped. But after doing the geolocation and geocoding algorithm, we know this lat long of this position. By knowing this lat long, we have to make some of the transformation from the sensor geometry to the map geometry. So that way, what we have to do, we have to transform from the SAR sensor geometry to the map geometry. Now you can see every image is every pixel is now projected to the earth. So now it is called the geocoded image. So this is the image is rotated, and because the SAR is the descending path and it is of right loop. Okay, so it has some sweeping in the horizontal direction. Okay, so this is the whole SAR data processing techniques what we have used in processing the SAR data. So it can be of form of level 0 processing, or it can be of the form level 1 processing. In the level 0, if any raw data product like pulsar is providing the level 0 data, So we can develop our own algorithms to focus the data. If any sensor is providing like L1 data, means it is of already the processed data, then if we will develop the algorithm for doing the range terrain correction, or we can do the ellipsoid correction, or we can use the software also, open source software also, for doing this type of corrections. Okay, so these are some of the data processing, but we have to do according to our product availability. Means if we are having the raw data, then we can use the signal processing algorithm to focus the data. If we already have the level 1 data, means SLC data, then we can use the geolocation geocoding algorithm to correct the geometrical corrections. Then finally, this data what we have to use for any application purpose, means this is the it is the geometrically correct and radiometric correct image. Okay, so that's all in this presentation. And in this presentation, what we have learned the level 1 processing, level 0 processing, and how to do the geometrical corrections of the